Hi friends, so today we begin lecture 34 on our helicopter dynamic series, and today I am going to discuss momentum theory in hover. Particularly we are going to focus on the induced velocity at the rotor disk and far downstream from the rotor disk. I am Dr. Ranjan Ganguly. Now let us look at the rotor disk which is given here, and there is a velocity through the rotor disk that's given by small v, that is the induced velocity at the rotor disk. Now far downstream or far below the rotor disk, this velocity becomes some quantity w, which we are going to try to derive, and far upstream of the rotor disk or far on top of the rotor disk, the velocity is zero. Now, according to actuator disk theory, this rotor produces a thrust which we call T, and that is the primary purpose of this rotor, to essentially generate the thrust so that this helicopter or drone is able to hang in the air. Now we call this far upstream station as station 0. Then we have station 1 and 2, which are just on top and bottom of the rotor disk. These are just given somewhat far away for clarity. Then far downstream there is the station 3. So essentially we have assumed the rotor to be an actuated disk with cross section A and the total thrust T. We also assume uniform loading on the disk. We say that V is the velocity induced at the rotor disk and W is the wake induced velocity far downstream of the rotor disk. Now some of the assumptions we have made. One is that a well-defined and smooth slipstream is assumed. And secondly, V and W are assumed to be uniform across the slipstream cross section. Also, we are going to assume that any effect of rotation created in the wake due to the rotor torque is neglected, and also that the flow is incompressible, that is, there are no shocks being generated, the Mach number is much below 1, it's below zero point 0.3 for example, and also that the fluid is inviscid, which means that there is no dissipation due to friction. Now, the assumption of incompressible flow is generally valid in hover because the flow is taking place very slowly. So the velocities v and w are relatively very small compared to the speed of sound. Remember, the speed of sound is somewhere 332 meter per second. But as far as the inviscid assumption is concerned, it's generally not valid because you are moving through air, and so the blades are going to encounter drag because air has a viscosity which goes with it. So that's generally a property of the fluid, and this viscosity causes friction. Now we are going to look at this viscosity aspect and the drag aspect later using a separate theory beside the current momentum theory. The momentum theory is not going to give us the drag created due to the profile effects or due to the effect of the airfoil section and the friction of the air going across or on top of the airfoil section. So let's now start deriving the equation. So the first thing we look at is conservation of mass. And essentially there is a mass flux through the rotor disk, and this we can denote by m dot is rho AV. So m dot is the mass flux, rho is the density of air, A is the area of the rotor disk, small v is the induced velocity. The density of air is generally taken as 1.225 kg per meter cube. The units of m dot are kg per second. Now conservation of mass says that mass flux is constant across the wake, so we are going to use this in our derivation later. Now the second equation is conservation of momentum, and here what we consider is that the rotor force is going to be equal to the rate of change of momentum. That's essentially Newton's second law. and therefore the rotor force T is m dot W minus 0, 0 being the velocity far upstream of the rotor. So remember, W is the velocity far downstream of the rotor. So T is m dot W, very simple equation coming to us from conservation of momentum. So this equation is very important. We can use it to calculate thrust. Now the third equation comes to us from the fact that work done by the rotor is equal to the change of energy of the fluid. So essentially this work done is going to be equal to Ke at station 3, which is far downstream, minus Ke at station 0, which is far upstream. So now the work done by the rotor is the thrust into velocity. Okay, that's the basic definition of work. And then this is equal to half m dot W square, because remember the Ke at station 0 is 0 because far upstream the velocity is 0. So this is our third equation, Tv equals half m dot W square. Now we are going to start putting these equations to work. So the second two equations are written here, coming from momentum conservation and energy conservation. And what we do is that from both these equations we obtain what is T by m dot and write it down. So the momentum gives us T by m dot is W, and the equation here gives us T by m dot is W square by 2V. So I get this equation W equals W square by 2V. From this equation I can straight away obtain W equals 2V. Now that's a very interesting revelation which is going to be used throughout rotor dynamics for obtaining the power required and so on. So this equation is very important, so we can write it down and discuss it more. The fact is that induced velocity in the far wake is twice that at the rotor disk, and that's what this equation is telling you. And interestingly, this is the same result as you obtain for an elliptically loaded fixed wing. So those of you who have studied the aerodynamics of fixed wing will recall this particular fact there also. Now let us go back to our rotor slipstream. And now we have found that W equals to 2V. So one of these issues has been resolved. So now we know that velocity far upstream is 0. At the rotor disk it becomes small v. Far downstream it becomes 2V. Now the second thing we look at now is what happens to this rotor slipstream itself. So here of course we know at the rotor disk the cross section is A1 and far downstream the cross section is A2. So we are going to try to figure out something about A1 and A2 from this equation. Now immediately we will realize that the mass flux is going to be the same because no mass is put in anywhere here, the same air is going through. So at the rotor disk m dot is rho A1V, far downstream m dot is rho A2W. So I can equate these two equations and I get A1V is A2W, which gives me A1V is A2 into 2V. So here I make use of the fact that W equals to 2V, and immediately I get A2 is A1 by 2. So that's the next derivation. That is why we draw the slipstream the way we draw it, that it is shrinking or constricting downward in the far downstream. So the area in the slipstream in the far wake is going to be half of A, where A is the cross section at the rotor disk, that is pi r square. So if you know the radius of the main rotor, you can figure out the radius of the slipstream from this equation. So today we derived a very important equation, W equals to 2V, which you should keep in memory because we are going to use that repeatedly. And then we have derived three more equations which we are going to use repeatedly. In the next lecture, I'm going to look at how Bernoulli's principle also can be brought in because we have to address the issues of pressure. Till now, we have been focused only on velocities. See you then.